this. Okay, I think we can start now. Hello, everybody. Today we have a pleasure to have a talk by Daniel Litim. He will tell us about interacting fixed points from quantum field theory to quantum gravity. Daniel, please, 1 hour.
Thank you very much, Irina, and thank you very much for the kind invitation to speak at your seminar series. So indeed, the plan of the day is to talk a little bit about interacting fixed points in quantum field theory and quantum gravity. Now, you might wonder, what the heck could be the motivation for that? So maybe as a particle physics, of course, I will have to start with the standard model. And what you see here is the standard model RG beta functions. They're running up to the Planck scale. Not much is happening, except that the quartic gets negative, so standard model becomes unstable. Okay, if we forget quantum gravity, then they run on until ultimately the hypercharge will run into its Landau pole, and the standard model as we know it will come to a natural death. Now, what's the thing with the standard model? See, we look for new physics at the LHC, and very heavily so, but believe it or not, the standard model is still the absolute best model on the market. We have no significant deviations from standard model predictions, small variations, tensions, which might be hints, but no new physics there. So at the present day, the state of affairs is the standard model is the absolute gold standard for all natural observations. We have indications for dark matter to come later, but this does not affect high energy physics predictions at the present energies. So the question is, how can the standard model be ultraviolet completed? Ultimately, because we know it is going to break down. So the classic standard idea for that, of course, is going back to Wilson, and it relates to the notion of a critical point. And indeed, if an extension of the standard model possesses an ultraviolet critical point, that would be sufficient to come up with a fundamental definition of quantum field theory. Or in other words, the theory would remain predictive up to arbitrarily highest energies. Now, of course, this notion is very well known. It has contributed significantly to the construction of the standard model, where this set of ideas is realized in, say, the strong and in the weak sector. However, we do not yet possess a completely satisfactory definition of a fundamental theory. Not for particle physics, and not in the realm in which gravity as a quantum theory is being included. Okay, so the idea of this talk will therefore be to ask this type of question in a different way and to allow ourselves to open up to the possibility that a fundamental theory of nature, be that on the particle physics side or possibly in gravity, that such a theory is possibly described fundamentally by an interacting ultraviolet critical point. Now, traditionally, we are used to think and talk about critical points mostly in the context of maybe thermal or quantum phase transition in condensed matter physics. Okay, these critical points relate to infrared, low energy phenomena, continuous phase transitions, or possibly even conformal or topological ones. Okay, so there's a large body of understanding of quantum critical phenomena in lower dimensional systems. Also, these theories have very intriguing and important links to the machinery available in the study of conformal field theory, because in principle, as soon as we have a quantum critical point, scale invariance at that critical point is lifted to become the full conformal symmetry. And this is now opening an entire extra dimension of structures, which in conformal field theory can be studied very systematically. So there's an interesting corner, fruitful corner for interactions with those technologies. Last comment here, there are also, and have been in the past 20 years, a lot of ideas revolving around, say, dualities such as ADS-CFT, which again require theories at critical points on the one side of the duality to then maybe link these theories to strongly interacting gravitational theories in IDS spaces. Good. So this, I hope, suffices as a motivation for why we are interested in quantum critical points. Now, the one central tool I'll be hammering on today is the renormalization group. And why is this so? The renormalization group is the tool which allows us to compute beta functions of running couplings. So in some sense, that's the most pivotal, critical cornerstone in this type of setup. So quantum field theory will therefore allow us to make predictions how couplings behave at largest or smallest energies. And in particular, this will us allow to investigate the existence or otherwise of fixed points. Now, what is an ultraviolet fixed point? Okay, maybe this plot is the simplest incarnation for that. Let me explain. So what you see here is the beta function for a fiducious theory, which has a coupling constant alpha. Okay, so you see that the beta function starts out positively. So it could be QED, it could be the minimal supersymmetric standard model, it could be for Fermi theories, it could be quantum gravity. So at small coupling, these beta functions will be positive. Invariably, this means that couplings, if we increase energy, and if we try to go to shortest distances and highest energies, couplings will grow. And as we know from QED, they actually can run into a Landau pole, causing the end of predictivity for these theories if the beta function remains positive. So the one conjecture about interacting fixed points, therefore, is the following one. It's the conjecture that quantum phenomena can arise which bend this beta function down again, so that we have an interacting, non-trivially interacting fixed point away from the origin. Now, the physics underneath this must be that strong quantum fluctuations, strong or weak, okay, cancel out each other in order to generate the fixed point. And the all-embracing question is, what can we say in some generality, and what do we know about the existence of this type of fixed point in quantum field theory? Good. So that was my motivation. And now let me tell you what I'm going to do for the remaining 55 minutes. So I will do essentially two things. Firstly, I will discuss what we know rigorously about weakly interacting fixed points, ultraviolet and infrared, in four-dimensional quantum field theories without gravity. So this is mostly a recap of results, okay, but I'd like to bring you up to speed with what we know there up until now. And in the second part of the talk, I will then investigate strongly coupled quantum field theories. So this is meant to cover, again, rigorous results, both in supersymmetry and in critical fermionic systems. And based on these findings, I will then explain what is our present-day understanding of the existence of fixed points in 4D quantum gravity. Okay, so let me begin with weakly coupled fixed points. Now, I'm talking 4D, four-dimensional quantum field theory. I'm imagining that we have vector fields, fermions, and scalars. So the standard stuff we normally see in the standard model. Okay, like nothing crazy here. Okay, no gravity for now. Weakly coupled means these guys are interacting with each other. So we have gauge interactions, Okay, we have Yukawa interactions and we have quartic interactions. Now, I've written down the most general Lagrangian retaining only the canonically marginal interactions. Why? The reason is this. At weak coupling, I'm going to now only talk about weakly coupled fixed points. At weak coupling, interactions are small, anomalous dimensions will be small, so there's no chance for quantum fluctuations to turn relevant interactions into irrelevant ones or irrelevant interactions into relevant ones. The only thing quantum fluctuations can do is they can turn marginal couplings into marginally relevant ones or marginally irrelevant ones. Okay. Therefore, we don't have to talk about mass terms. They will be relevant always. We don't have to talk about higher dimensional interactions. They will be irrelevant always. Okay. So that's, say, maybe the key simplification here, thanks to recoupling. Good. Other than that, we make no assumptions. So we investigate the most general four-dimensional quantum field theory there is. Now, let me introduce this concept of theory space then. Okay, I told you which type of interaction terms I retain in the Lagrangian, and we see Yukawa, quartic, and gauge interactions. Okay, and so the theory space in some sense, you know, are these independent couplings which appear in the Lagrangian. And so clearly the theory can have fixed points which are either where everything is zero, so the free fixed point, but that one is perhaps a bit boring. We can have interacting fixed points where perhaps only the gauge coupling is non-zero. This is what normally is known as the Banks-Sachs fixed point. There also exists a version with charged scalars, okay. We could have fixed points where only the scalar couplings are non-zero. We can have fixed points where scalar and Yukawa interactions are non-zero, or we could end up with fixed points where all these type of interactions are non-zero. So there are some possibilities here. Good. Now let's make a diagram. So what I'm showing you here is the three types of couplings we have, and yes and no indicates whether they are switched on at a fixed point or not. Now, my claim is you can systematically and rigorously analyze the most general such theories. And what you find as a result is this. You find that if and only if your theory has non-abelian gauge interactions, only then you will be able to find weakly interacting fixed points. Important result number one. Second, of course, you have no fixed points if these guys are absent. Okay, so there exists no such thing as a purely scalar fixed point or a scalar Yukawa fixed point. And there also do not exist weakly coupled fixed points involving abelian interactions. Okay, good. That's the first important result. Now, let's look into the type of fixed points in a little bit more detail. So the first one here says gauge non-zero, Yukawa and quartic zero. That's the well-known Caswell Banks-Sachs fixed point from the mid-70s. Okay, it's an infrared fixed point. So your theories are asymptotically free. Okay, and if it's not QCD, but say QCD with a couple of more fermions, yes, then your theory can actually achieve this type of infrared fixed point. Similarly, if you replace the fermions by charged scalars, you can have a Banks-Sachs infrared fixed point. Now, in this list, there's one thing which is truly unexpected. And this comes when you look into the third column here. So this is where all three types of interactions are switched on. What happens here is that not only can these type of fixed points exist, but for the first time, the table tells you that this fixed point can actually be an ultraviolet fixed point. And that was a kind of unexpected novelty. Back until then, people thought that once asymptotic freedom is lost, theories can no longer be fundamentally predictive. But it does turn out that even in these type of innocuous theories, okay, you can give up asymptotic freedom and the theory remains well-defined thanks to an interacting fixed point in a gauge-Yukawa type theory. Now, let's look a tiny bit more. So there are some references. Okay, good. I will not run to those things. Okay, let's look now that we have these pieces of information, let's look a tiny bit more with a tiny bit more detail into it. Okay, so we were saying we have these three types of examples, three types of interacting fixed points. Okay, now fixed points can still be free. They have not appeared here, but the Gaussian fixed point always exists. So in the end, we end up with 5 types of possibilities, namely asymptotic freedom, such as in QCD, in which case the beta function would precisely look like this red curve. Asymptotic freedom with a Banks-Sachs fixed point, the beta function would look like this. Asymptotic freedom with a gauge-Yukawa infrared fixed point, the gauge beta function would look like this. Okay, so this is perhaps not absolutely new. Okay, but what was new is now the fourth case where we see that the theory is not asymptotically free, but infrared free. Okay, so exactly the type of example which I discussed in the beginning. Okay, I would suggest that the gauge coupling here would want to grow if we go to higher energies, but no, it's not growing because quantum fluctuations bend this beta function now. Okay. And finally, the fifth example, of course, is infrared freedom, such as in QED, where we also don't have any other fixed point. Okay, good. So a priori, these are the 5 basic possibilities. Okay, and now, based on this, you can construct any weakly coupled quantum field theory you want. Take a product gauge group, make your interactions as complicated as you want, but broadly speaking, the only structures, fixed point structures, which you can get out of it are combinations of these types of beta functions, so higher dimensional coupling spaces with these basic samples. Good. Okay, now for each of these cases, you can, if you want, plot a phase diagram such as these. Okay, so for the 5 cases I was mentioning, you can now plot in the space of gauge coupling, which is the lower axis, and Yukawa couplings, which is the vertical axis. You can plot a phase diagram. You will probably recognize diagram 1 as something that looks like QCD, asymptotic freedom, and infinitely many trajectories running out of that UV fixed point down to lower energies. Now, if you look into different types of theories, they may additionally have a Banks-Sachs fixed point, like in figure 2, or a Banks-Sachs and a gauge-Yukawa fixed point, such as in figure 3. Yes. But then, once you give up asymptotic freedom, okay, so once your Gaussian free fixed point no longer has outgoing RG trajectories, okay, you still can find perturbatively, rigorously controlled interacting fixed points such as here, okay, or if you don't find them, well, then bad luck, then you will end up with the phase diagram shown in figure 5, okay, which tells you you only have this infrared fixed point, but the theory most likely cannot be ultraviolet completed. Okay, now let's have a quick look into this perhaps most interesting case, case 4. Okay, so case 4, remember I was telling you the beta function of that quantum field theory looks exactly like this. It has an ultraviolet fixed point, and the main feature of this fixed point is that this fixed point is perturbatively weakly coupled and sufficiently close to the origin that perturbation theory is still reliable. Now, what type of quantum field theories do have this fixed point? We have found 3 rather large type of families. Okay, so if you want to play around with models and have some fun with ultraviolet fixed points, the recipe to get them is take an SUN gauge theory, couple them to Dirac fermions, and give them Yukawa couplings to mesons. Okay, now if you have a sweet spot for Majorana fermions, yeah, that can also be done, because then you take an SON gauge theory, couple them to Majorana and mesons, or to a symplectic gauge theory. Okay, doesn't matter. All these settings for sufficiently large n, so that the theory is weakly coupled, give you precisely this type of phase diagram with a rigorous ultraviolet fixed point at weak coupling. Good. So, what is it that we learn from this? Okay. So let me discuss a couple of implications. So the first implication is maybe from the viewpoint of particle physics. Okay. We do know that ultraviolet complete theories, okay, require an ultraviolet fixed point. And the message which now comes out of this analysis is that this can be achieved either via asymptotic freedom or via an interacting UV fixed point. Fine. But in either case, we do necessarily need non-abelian gauge fields. Okay, so the somewhat absolutely surprising novelty in this result is that asymptotic freedom and asymptotic safety are two sides of one and the same medal, non-abelian gauge fields. If you have them, you have a chance of achieving asymptotic freedom. If you have them, you have a chance of achieving asymptotic safety, a weakly interacting fixed point in the UV. If you don't have them, you're done. You can go home, all over, story finished, nothing else that you can do. Okay. Now, why is that interesting, perhaps? Okay. So people understood very well the importance of asymptotic freedom. A lot of model building had been done to try to extend this standard model, okay, in the spirit of finding a complete asymptotically free extension of the standard model. But now that we know that from first principles, there may exist extensions of the standard model which actually have an interacting ultraviolet fixed point, this fact is opening up new territory to search for extensions of the standard model. This is something which didn't exist as a search strategy or anything like that. It's simply because people weren't aware that there is territory to be explored. Now we do know that, and it is an interesting thing to play around with these ideas. So a couple of works have appeared addressing some of the open riddles in the standard model, such as anomalous magnetic moments, flavor anomalies, and vacuum stability. Okay. Now, second implication, okay, from the viewpoint of statistical physics, maybe. It was an extremely fruitful program in three-dimensional critical phenomena to classify genuine universality classes characterizing critical points. Now that we have this structured understanding of interacting fixed points in 4 dimensions, okay, it is now in reach to perform a similar classification and systematic analysis about critical points in 4-dimensional theories. So this, I think, will be a very interesting and important task. Now, there's a second spin to what I just said, and that relates to the field of conformal field theory. And the reason for this is that any weakly coupled 4-dimensional conformal field theory must contain non-abelian gauge fields. How comes? Well, the argument goes like this. Polchinski, Luti, and Ratazzi over the years have come up with an important proof establishing that any quantum field theory which is under perturbative control in the deep UV asymptotes to a conformal field theory. What does that mean in our context? It means that all the weakly interacting fixed points of which I have just spoken, all of these correspond to unitary conformal field theories. Now, This is the fact which implies that any weakly coupled four-dimensional conformal field theory intrinsically must contain non-abelian degrees of freedom. Now, this is something which is absolutely not visible or detectable if you try to think about conformal field theory within the conformal field theory standard language, where you start with primary fields, all of which are gauge invariant objects, okay? However, this analysis now additionally explains us that underneath these primary fields must be non-abelian gauge fields. Okay, so I think this is an interesting territory in its own right to look into, okay, but that's a tiny bit besides the mainstream or main thrust of my talk today, okay? And as I said, this was meant maybe as a recap and maybe as a warm-up as to what we understand rigorously about weakly interacting fixed points. So now I want to change gears and I want to talk about strongly coupled fixed points, okay? Now, strongly coupled fixed points is a total nightmare. As you probably have anticipated, okay, it's not a big surprise. Strong coupling physics is very, very challenging. Why is it challenging in this context? It's challenging because strong interaction means large anomalous dimensions, okay? Strong coupling, we need to control strongly coupled theories. They will have large anomalous dimensions. We do no longer know which types of interactions will be relevant, marginal, or irrelevant. Okay? We couldn't even put such theories on the lattice, because if you were to be putting it on the lattice, you need to know beforehand which types of interactions will be relevant and which will be irrelevant. Okay, so this is why progress in the understanding of strongly coupled theories has been somewhat limited. And I will highlight a couple of corners, however, where we do have some rigorous understanding. So the first corner is supersymmetry. I'm talking about four-dimensional supersymmetric theories, n equal 1, okay? And you might ask yourself, oh, yes, what has supersymmetry ever done for us? Okay, why do you think supersymmetry is useful for strong coupling? Well, there are three central points for that. What is supersymmetry doing for us, which non-supersymmetric theories cannot deliver? In supersymmetry, we have extremely powerful non-renormalization theorems. They dictate exact renormalization group equations for Yukawa interactions. Also, we will not have to scratch our heads with quantic interactions. Second, with supersymmetry, we have infinite order renormalization group equations at our hands. Okay, this goes back to the seminal work by Novikov, Schiffman, Weinstein, and Sakharov, okay, and also relates to recent works done along similar lines, where these ideas have been substantiated now in significantly different RG schemes. So this means that we have essentially non-perturbative RG beta functions for these theories, which we don't have in n equals 0. Finally, A maximization. Now, what the hell is A maximization? Okay, here it comes. A maximization is this. If we have n equal 1 supersymmetry, the conformal algebra suddenly has one additional global charge called the R symmetry and the corresponding R charge. Now, the absolutely intriguing thing with this R charge is that the value of the R charge relates to the chiral superfield anomalous dimension of all superfields. So, in other words, if we can compute from the conformal algebra these R charges, we non-perturbatively know their values at interacting fixed points. That's a piece of information which we can reinsert in step 2, okay, to get fully non-perturbative RG equations. And those we can solve and can then ask questions for interacting fixed points. That's what I'm going to do now. Okay, so the type of theory I will be looking into is a semi-simple supersymmetric gauge theory, SUN cross SUN, two different ends. I allow them to have some superpotential with U-cover interactions. Okay, the chiral superfields have certain charges. Doesn't really matter. It's a vanilla example, and what I'm going to talk about as a result is going to work for very many of these theories. Okay, so there's nothing particularly tuned in this setup. You can now, if you want, investigate this theory A in perturbation theory, which we did up to 3 loop, B non-perturbatively using the methodology I just described. Okay, we have checked that everything agrees with each other if we re-expand the non-perturbative results in perturbation theory. Now, what is the result? First of all, look at this phase diagram. This is how the phase diagram of the theory looks like. Let me explain. So this is gauge coupling 1, this is gauge coupling 2, this is the origin of the coordinate system. So we see the free theory fixed point, but now it comes. One sector looks asymptotically free because it has outgoing trajectories. The other sector is infrared free because it has an incoming trajectory. So what this means is that the theory is not asymptotically free, full stop. This Gaussian fixed point cannot be used to fundamentally define this theory. If you want to have a physics example where this is happening, you can think of the minimally supersymmetric standard model, okay, where this is SU2 and this is SU3. Yes, SU2 becomes unstable in the MSSM. So, how can this type of theory develop an interacting non-trivial ultraviolet fixed point? Well, here it comes. The theory can develop a fixed point where one of the gauge couplings is non-zero. The other one, alpha 2, could very well be 0. But what's happening here is that the gauge coupling alpha 2, which was marginally irrelevant at the Gaussian fixed point, suddenly becomes marginally relevant at the ultraviolet fixed point. Therefore, and only therefore, this fixed point qualifies as an ultraviolet fixed point for this quantum field theory. Okay, so we will now be talking about this fixed point here. Okay, this fixed point allows, if this fixed point wouldn't be there, the gauge coupling alpha 2 can never be switched on. Okay, so only because we have this fixed point, yes, we are allowed to think of this theory as a truly fundamental theory. Okay, so what now needs to be done is, see, we have a couple of parameters, SUN1 cross SUN2, so these multiplicities will be parameters. We have a certain number NF of chiral superfields. We have some other spectator chiral superfields with multiplicity NQ. So we have a couple of field multiplicities. This will be parameters, okay? And as functions of these parameters, we want to understand conditions so that this type of fixed point exists. Let me now show you the result. The result is what we call the non-perturbative ultraviolet conformal window for this fixed point here, this one, okay, to exist. Let me explain what you see, okay? So the lower axis is epsilon. Epsilon is this parameter, and you can think of it as the one loop coefficient of the alpha 1 gauge coupling, okay? So if you tune the ends such that epsilon is a small number, we would be in the territory of perturbation theory. However, if epsilon gets big, the theory will be non-perturbative. Now, the vertical axis here is the number capital R, and that's just the ratio of the size of the two SUN gauge groups, okay? N2 over N1. Now, the color coding tells us that there's a third dimension, a third direction, okay? For another parameter, which I haven't written down, okay? Which is unimportant, but it just is meant to indicate that there's some further depth with respect to a third parameter. Okay. So in some sense, this is meant to be a three-dimensional conformal window in parameter space. Good. Now, what's the important take-home message from this investigation? The first one is, in the vicinity of epsilon close to 0, we are in the domain of weak coupling. And this is where we have computed things up to through loop, and everything is consistent. So we know the size of the conformal window the way perturbation theory would predict it, okay? Now, the most important result perhaps is to realize how large the conformal window has become now that we are able to compute non-perturbatively. That's maybe the first observation. The second observation is that you see there are parts of the parameter space down here, okay, ratios as n2 over n1, which suddenly become available, which have not been available in perturbation theory. Okay, so we truly see non-trivial, non-perturbative effects going on, which enable these the existence of these strongly interacting fixed points, which do not have partners in perturbation theory. They do not continuously connect with anything we find in ordinary perturbation theory, because there is no partner to that. Okay.
Oh,
now,
excuse me, Daniel, may I ask you a very naive question? What is the meaning of different colors in this plot? Yes. And it's okay.
Yes, Irina, thank you very much for that the question. So there is a third parameter characterizing these models. And so the color coding tells you the depths of the plot. Okay, so it tells you something, how many different values for this additional parameters are we allowed to take to still sit inside the conformal window. So light blue means it's not very deep, and dark red means it's very deep. Okay.
Okay, thank you.
You're welcome. Okay, so let me now quickly mention this lower end. Okay, how comes that this diagram comes to an end? So you see epsilon, which is in perturbation theory a very small parameter, can go up to -3/2, which is highly non-trivial. And the reason why we need to stop there is this end here is dictated by bounds on unitarity. Okay, so this is where chiral superfield anomalous dimension becomes so large, yes, that certain new bound states corresponding to free scalars can be built, and then the analysis of this theory needs to be done in a different manner, also incorporating these scalar degrees of freedom. Okay, so what are the implications of this first analysis here? A, the message is we can non-perturbatively compute UV conformal windows. B, they are significantly larger than we could have had expected based on perturbation theory only. 3, by and large, the central phenomena in the weakly and strongly coupled regimes do look similar. The theory is not taking a completely different shape. Okay. Now, final point, and that's perhaps a proof of concept. Okay. Since these fixed point exists at strong coupling, it actually means that they exist even for small numbers of field multiplicities. So these type of non-perturbative fixed points, you can find them in, say, SU3 cross SU2. You could possibly find them in SU2 cross SU3 type gauge theories. Okay, you don't have to take any large n Veneziano limit to have them. Okay, so that was non-perturbative example number 1 in 4 dimensions, thanks to tools from supersymmetry. Now, I want to talk about a second example. This is an example from 3 dimensions. three-dimensional critical fermions. Now, what's the story here? Okay. Well, 3D critical theories, of course, they have extremely many applications in condensed matter physics. Okay, fixed point tend to be of the Wilson-Fisher type and variation thereof. Okay. So they have typically very many applications. They're also of relevance for the ADS-CFT conjecture, like because critical bosons or fermions in 3 dimensions are a 3D conformal field theory, and they relate to higher spin gauge theories on ADS4. So that's an interesting twist, and that has resulted in quite some activities a couple of years back. Good. Now, what's the angle for us? The angle for us is we want to talk about critical fermions, so think about Gauss-Neveu. Okay, so you take a number of fermions, give them a UN symmetry, and you write down 4 Fermi interactions, psi bar psi squared. Now, this is to some extent the role model quantum field theory for something that is perturbatively non-renormalizable. Okay, so back in the days, you would have thought, okay, I need to run away because this theory, I can never fundamentally make sense out of it. Okay, and technically, that's associated to the fact that the canonical mass dimension of this relevant coupling is negative. So in 3 dimensions, it would be -1. Okay. However, quite some time back, people have understood that the theory is fundamentally well-defined. And the reason for this is that the theory develops an interacting UV fixed point. So what I'm going to discuss next is I want to revisit this theory as a toy model for something which becomes asymptotically safe. Okay, so in the spirit of what we were talking about before, you can now think of how the beta functions for a 4 Fermi coupling could look like. And because of its canonical mass dimension, it will start out positively. And ordinarily, you would have thought this theory cannot possibly be well-defined in the UV because we run into a pole before we reach highest energies. However, the story here will be precisely that non-trivial quantum fluctuations of these fermions bend this beta function down to generate a rigorous, strongly coupled UV fixed point. Okay, so this is what I will be discussing next. Now, the only one upgrade I will on top add into this is I do allow even fundamental 6 fermion interactions. And now, people haven't done so in the past because the 6 fermion interactions, for once, it's even less relevant than a 4 fermion interactions. It has canonical mass dimension -3, so how can that ever become a relevant parameter? Okay. Second, this type of interaction would break chiral symmetry. And the standard law is we have this quantum field theory, and one of the nice things is when H is 0, you know, it's chirally symmetric, and mass, fermion mass, needs to be generated dynamically thanks to dynamic chiral symmetry breaking. Okay. Now, here we look at that theory from a slightly different angle. We allow ourselves to not start with chiral symmetry from the outset. And we may or may not write down a mass term if we want it. And we will retain this 6 fermion interaction. Now, the tool I am going to use to investigate this theory is goes back to ultimately ideas by Wilson, maybe upgraded later on by Polchinski and also Wetterich and others. And in these days, these technology is known as maybe functional renormalization. And it works by introducing by hand kind of infrared cutoff to your theory. But the virtue of doing that is that you end up with some form of non-perturbative, but a priori exact functional flow for your quantum field theory. Now, why is this intriguing for our purposes? This is intriguing for our purposes because it so turns out that this RG flow can be solved rigorously and in closed form. Okay, so this ordinarily is not possible. Now, the reason for why this is possible here is because we take the limit of infinitely many fermions. And in this particular limit, additional simplifications will arise so that we can solve this non-perturbative RG flow exactly. And that's what we want to do because we want to have rigorous results and rigorous understanding about the existence or otherwise of fixed points. Okay, so let's have a look into how all that looks like. Okay, now, so my view will be again to now look into the theory space. Okay, and so remember, when we were talking about weakly coupled theories, I was only writing down the canonically marginal interactions. But now we are talking about a strongly interacting theory. We are no longer allowed to just retain relevant interactions. We must even retain classically irrelevant interactions. Then we may solve the theory if we can. And then the result which incorporates quantum fluctuations is going to tell us which of these interactions in the quantum world are going to be relevant, irrelevant, or marginal. So let's have a look at that. This is our theory. What's going to happen? What's going to happen in the quantum world is this. First of all, the 4 Fermi interactions, which is classically irrelevant, is going to become relevant. Okay, so this is quite significant. It's an operator of canonical mass dimension -1. So the scaling, however, changes completely due to quantum fluctuations. Now, the surprising thing is that this is not even the end of the story. Now you can look into the 6 Fermi interaction. This operator, which is massively irrelevant, canonical mass dimension -3 in 3 dimensions, actually becomes exactly marginal in 3 dimensions. Again, a highly non-trivial, non-perturbative effect. And then you find all higher order interactions are irrelevant classically and remain irrelevant quantum mechanically. So now let me spare you with some of the details here, okay? Like, but let me tell you one thing about this theory. One thing which one may learn by looking into these non-perturbative RG equations for the mass term. So the mass term, please don't get confused. Lambda 1 is the fermion mass. Okay, a funny name for a mass. I apologize for that. Lambda 2 is the 4 Fermi interaction, and lambda 3 is the 6 Fermi interaction, and then you get similar type of equations for all higher 2n fermion interactions in this theory. Okay, so let me highlight 2 things. The first thing is that when the mass is equal to 0, so lambda 1 equals 0, actually this is an exact fixed point of the RG. Now, this is kind of funny. Why is this funny? It's funny because normally you think, I have a quantum field theory where chiral symmetry is manifestly broken. We have 6 fermion interactions in there, okay? Still, it's enough to put the mass to 0, and masslessness is guaranteed because it's an exact RG fixed point, okay? So mass is not generated by the chiral symmetry breaking interactions. Okay, they don't couple back. Lambda 3 is not coupling back to the flow. Good. That was a small surprise. Okay, now let's put the mass to 0 because we are interested in critical points. If we put the mass to 0, these complicated beta functions collapse to something which suddenly looks simple, namely this. Let's start with the 4 Fermi interaction. You see, here's the 4 Fermi interaction. Okay, and so you understand that this type of beta function can exactly have two fixed points, lambda 2 equals 0, and lambda 2 such that this prefactor is 0. That's the 4 Fermi fixed point. But now comes the small surprise. Okay, if you now insert this fixed point into the 6 Fermion beta function, you will see that the prefactor vanishes automatically. You don't have to do anything. Okay, so what this teaches us is that there is a non-trivial, see, these constant terms here come from the canonical mass dimension of the 6 Fermion interaction. And now the contribution lambda 2 times lambda 3 comes from quantum fluctuations. But these rigorously and exactly cancel the canonical mass dimension. This is how the 6 Fermion coupling becomes exactly marginal. Okay, it's rare to see these type of things happening in a quantum field theory, and it is very important to be able to have some rigorous control over approximations, or otherwise you wouldn't be certain about the correctness of the result. Now, what you now could do is you can sit down and say, let me plot the phase diagram. Okay, so what you see is it will look like this. Okay, so we see, for example, the fixed point, the well-known asymptotically say fixed point in the chirally symmetric theory, which would be this one, 6 Fermion coupling equals 0. Okay, you can flow to the free infrared fixed point, but then there is an entire line of fixed points, because you are allowed to switch the 6 Fermion coupling on, because its beta function is rigorously 0. It's exactly quantum, exactly marginal. Okay. Now all these fixed points are strongly interacting. Okay. And this strong interaction leaves its fingerprints in non-trivial quantum anomalous dimensions. Here I have computed them for you. So what you see here, let me start with the red line. The red line is the free infrared fixed point. So here you have classical scaling dimensions for all operators in the theory. Okay, so the dot corresponds to a value for these operators. They're all on a line. Okay, so you see one has a negative scaling dimension. That's the mass term. This is for Fermi interactions, which in the infrared is irrelevant. 6 Fermion irrelevant, 8 Fermion irrelevant, and they are increasingly irrelevant. However, in the ultraviolet, the scaling dimensions are significantly different. And there you find this blue line. And you see in the ultraviolet, you have 1 relevant, 2 relevant, and an exactly marginal coupling. This is the mass term, which is always relevant. This is now the 4 Fermi coupling, which has become relevant, and this is the 6 Fermion coupling. All the others remain irrelevant. So we notice that this ultraviolet fixed point, yes, is strongly interacting, and we deduce this from the order 1 shift in scaling dimensions, which is a result of the intrinsic interactions in the theory. Okay, now what are the implications of this result? Okay, we have a proof of concept, which is that canonical, non-trivial canonical dimensions of operators can indeed be cancelled or overcome by strong quantum fluctuations. We have also learned that all field monomials in our theory space need to be retained, okay, to make sure that we actually obtain the correct result. There's a tiny bit more to this result, which, however, I would like to skip at this instance, or else I will not have enough time to say 2 things about gravity. Okay, but let me mention that our results now offer new conformal field theory duals for higher spin gauge theories on ADS4. So previously, people have found Vasiljev duals based on the chirally symmetric solutions as the CFT boundary. But now we have an entire family of chirally non-symmetric boundary conditions. And it would be interesting to understand whether this leaves an interesting fingerprint on the higher spin gauge theory side in Vasiljev's type series. Okay, so now my last point. Okay, I've shown you up until now, I've shown you results which to some extent are rigorous, either perturbatively controlled, rigorous methods in supersymmetry, rigorous control thanks to using large N techniques. None of this can be applied in 4D quantum gravity. Okay, but nevertheless, we will try to use some of those ideas to gain an understanding. So let me explain. First of all, I probably don't have to remind everybody of what kind of theory gravity is. Maybe from a quantum field theory point of view, the one thing which is sticking out, so if you ask yourself what's really new with gravity, okay, so some people say yes, of course, it's the territory, it's the arena on which quantum field theory takes place. Yes, that's to some extent true, okay. But in some sense, like what's really new is that you have a new type of degree of freedom, and that's spin 2. So we've been talking up until now spin 0, 1/2, 1, but spin 2 is maybe the novelty. Spin 2 immediately implies that the relevant coupling constant has negative canonical mass dimension. So in that sense, gravity has some structural similarity perhaps with the fermionic theory we were discussing a minute ago. So simply based on this reason, we must expect that if this theory by some intrinsic mechanism develops an interacting fixed point, then that fixed point is likely to be strongly coupled because it needs to generate strong anomalous dimensions so that canonical mass dimensions can be overcome in exactly the same type of way as we've seen it in the fermionic examples. Good. Now, what we might expect, of course, so the motivation or the expectations of this, they really go back to the old works by Steven Weinberg, but also Kawai, Gastman, and Christensen from the late 70s, okay, who studied gravity in 2 + epsilon dimensions and which has motivated a lot of these modern studies in 4 dimensions, okay. So in 2 dimensions, we know that this type of UV fixed point exists kind of perturbatively, but the $1 million question, of course, is whether any of this can survive in proper 4 space-time dimensions. So if we were to be comparing it with the graph, which I've been showing you time and again, okay, so it's the exact same plot, of course, yes, but now you would want to think of it in terms of Newton's coupling, scaled appropriately and to make it a dimensionless coupling, so let's call it alpha Newton then. We do know that thanks to its canonical mass dimension close to the Gaussian fixed point, its beta function necessarily must be positive. And again, the big question is, are quantum effects strong enough to bend this beta function down and generate a new fixed point? Okay, so in that sense, of course, close to the Gaussian fixed point, we would be back in the realm of classical GR, okay, which in this language would be the infrared fixed point of that theory. But if gravity is so kind to us and willing to exist as a proper quantum field theory, then maybe it's going to generate a known interacting fixed point, and which we then could use to define a concept and the notion of quantized gravity. Okay, so now I will try to use the same, say, conceptual framework when I now formulate fixed point searches in this type of theory. So the one thing I need to start with is I have to explain you what is my theory space. So the idea in asymptotic safety would be the only thing we know, well, we don't even know that, but like the minimal assumption is the graviton continues to be the carrier of the gravitational force. Now, how the quantum fundamental action looks like, we don't know. So this is part of the question. So therefore, we need to write down maybe all possible curvature invariants, okay, that can be formulated in a theory of gravity. Yes, so you could start with a cosmological constant Ricci scala, 2, 3 more powers of curvature, maybe covariant derivatives of curvature and whatnot. So a priori, that's the operator space in which, if a fixed point exists, it must be sitting somewhere in that operator space. Good. Fixed points can be free or interacting, so this doesn't change, of course, okay? But the important question is, how can we ever find such a fixed point? Now, the philosophy, see, we have very little guidance. The fixed point is likely to be strongly interacting. So the only thing we have at hand is we know how the theory scales classically. We know classically the cosmological constant and the Ricci scala are relevant operators. The fourth order interactions are classically marginal and the higher order ones are irrelevant. But in the quantum world, it is not warranted to take this as a presupposition. So we need to retain higher curvature invariance and do a proper search. And after that search, we maybe can then make an educated decision as to, we have a more educated understanding of what is really relevant and what is not. So just to illustrate a bit how this philosophy works, so let's look into one simple example. Imagine quantum gravity would be as simple as higher powers of Ricci curvature. Then a search strategy would consist, in full analogy to how these fermionic theories have been investigated, would consist in starting maybe with the Einstein-Hilbert action, and then order by order include higher curvature invariance. Okay, so what this means is that you derive your RG flow equations, you look for a fixed point, you evaluate scaling dimensions, you put this data in a table, then you include the next highest order curvature invariant. You redo the same thing, you plot your data, you retain the next highest order, and so on. Okay, and maybe if you see that your fixed point data converges with a reasonable pace, and if you see that results stabilize, even if you include higher and higher order interactions, then you can find some credibility for your results. So in this case of f of r gravity, you see a lot of people have contributed to this research, and studies have been pushed now to very high order in Ricci curvature. Okay, and the result, if you plot everything on top of each other, looks like this. Let me try to explain that plot for you. Okay, so what you see are the non-trivial scaling dimensions of a gravitational ultraviolet fixed point. The color coding here means that we have investigated this model with only Einstein-Hilbert interactions, light blue, Einstein-Hilbert plus r squared, Einstein-Hilbert plus r squared and r to the fourth, and so on up to Einstein-Hilbert and all interactions up to r to the power 70. Okay, now then we computed all those scaling dimensions and we see that the results converge very nicely. There are no massive fluctuations in the result. We see that there are 3 scaling dimensions which always come out as relevant. These are essentially cosmological constant, Ricci scala, in this case r squared interactions. All the other interactions come out with scaling dimensions which are irrelevant. Okay, and more importantly, they all come out as increasingly irrelevant the larger their canonical mass dimension is. Now, what this is suggesting, this suggests that a gravitational fixed point may exist, that a feature of such a gravitational fixed point is that higher order scaling dimensions get moderate quantum corrections. They don't shift significantly away from Gaussian scaling, but a little bit, noticeably. The only other thing which is noticeable is that we get 3 relevant directions. So the fourth order interaction, which classically is marginal, becomes relevant in the interacting theory. So this is the take-home message, say, from this extensive investigation in F of R gravity. Now, of course, you will quite rightly object and tell me, Daniel, quantum gravity isn't F of R. Yeah, I agree, it probably isn't. So how good are these results? Like, what do they really mean? Yeah. So it's totally true that in principle, you would want to investigate the entire operator space of possible invariants. It's only that this is presently way too difficult. So what we do is we try to investigate these models as good as it can be done with today's technology. That's where some of the limitations in these investigations are coming from. Now, in order to overcome them, however, or at least to explore what could be beyond F of R type modeling, what you can do is you can say, okay, let me investigate theories which additionally have Ricci tensor interactions. Of course, the fluctuations of Ricci tensors are different than the fluctuations of Ricci scalar interactions, and this could leave in fingerprints. So let's see what comes out of it. We performed the very same type of search strategy, okay, including increasingly higher Ricci tensor interactions, okay, powers of Ricci tensor. And again, what we find is that we end up with three relevant operators, Einstein-Hilbert plus Ricci tensor squared. After that, they become increasingly irrelevant. So the qualitative picture, which we found with F of R, persists if we randomly, but like in some model, play around with Ricci tensor interactions. Good. Now, the latest thing in this development, which goes back to work with Yannick Kluth a few years back, is to make the same, but now really with Riemann tensor interactions. I'm showing you this because one thing which is potentially new is happening here. So we now take higher powers of Riemann tensor interactions into account, and you see a very stable result. So these are really up to 144 powers in Riemann tensors. Okay, so Yannick has been really putting a lot of effort into pushing these investigations to the highest order possible. Okay, and you see, so results converge reasonably rapidly. Okay, but there's one thing which is noticeable. So you see there is a fourth operator which in this setup has become relevant. Okay, so there is possibly something related to Riemann tensor interactions, okay, which is acting in the background and which could possibly change the understanding of a UV fixed point in gravity, because it does make a difference whether your theory has 3 or 4 relevant fundamental couplings. Now, I think I'm a tiny bit over time and I should probably come to an end shortly, okay? So I have maybe 1 or 2 things which I would like to show you as part of an outlook, but would 5 minutes be fine?
Okay, yes, 5 minutes would be fine.
Yeah, okay. Thank you very much, Irina.
You're welcome.
So I've showed you those explorations, okay, so where we really have putting in a lot of effort to understand how higher curvature interactions affect and maybe stabilize the fixed point which people have found in the Einstein-Hilbert theory. And you could now say, okay, let me quickly compare those. And this is a graph which is comparing them. Okay, so let me explain. G star is the value of the dimensionless Newton coupling. Lambda star is the value of the dimensionless cosmological coupling. Now you have a couple of dots. EH means Einstein-Hilbert. So this is what you found in the Einstein-Hilbert approximation. Blue and red means the same type of investigation, but slightly different technical parameter choices. So the deviation of blue and red gives us an idea of what could perhaps be an uncertainty in the value of fixed point couplings. So what we first see is like that Einstein-Hilbert gives us coincidentally a fixed point of order 1. Then we can investigate these f of r extensions I've shown you, and you see those are even a tiny bit more weakly coupled, okay? But that would look like a very sensible higher curvature UV completion of Einstein-Hilbert, okay? Now, if you switch on Ricci tensor or Riemann tensor interactions, however, we realize that the deviations are much larger. So here we see that the cosmological constant gets bigger due to Ricci tensor interactions, and Riemann tensor interactions may even push it up to here. It makes the theory much more strongly coupled. So presently, we can say that we have a couple of candidates, both of Ricci or Riemann nature, which could UV complete the Einstein-Hilbert results. There's possibly also this strongly coupled fixed point over here, which can do that. Which of these is ultimately the correct one? This needs more work that we cannot presently decide from what we've done. So what type of work could go forward and help with this decision? Okay. Or in other words, what comes next? So I think an interesting step has been made recently together with Yannick. So what we managed to do is we now managed for the first time to derive very, very general RG equations, namely RG equations for the models of quantum gravity whose action is the most general function of the Riemann tensor and the inverse metric. Okay, this is highly, highly non-trivial. What's the non-trivial thing in this? Normally, it works the other way around. Normally, you write down your action. Okay, I have those many operators. Then you compute second variations. You compute your RG flow. You do the heat kernel traces. Okay, and then you get the beta functions for all your couplings. Right here, okay, we do not even have to specify the form of this Lagrangian. Why is this possible? This is possible if you use maximally symmetric backgrounds to compute the operator, the heat kernel of the various second variations in the operator traces. Okay, and now for those who are maybe familiar with this or have heard about this, there's an important technical point here, which is that the second variation of the most general action, which depends on the Riemann tensor and the inverse metric, okay, if evaluated on maximally symmetric backgrounds, it boils down to only 3 functions of curvature, where A, B, and C are invariant tensors, so that's an orthogonal decomposition, okay, but we end up with 3 free functions. Now, this is a super powerful tool now, because what this will allow us is that we can map every curvature invariant which we can possibly write down. Okay, so here you have the list of independent curvature invariants with increasing canonical mass dimension. We can compute the corresponding parameters that have to be plugged into our flow equation, and thereby we obtain the flow equations for the couplings of these curvature invariants. Okay, and so this tool is very powerful. It only needs to be applied. So hopefully, we've started applying it, but so this will allow now a very systematic investigation of the space of curvature invariants in these theories. Okay, so maybe to give you one example, if you compute the second variation in these general theories, remember, the action is a general function of the Riemann tensor. These type of theories can, in principle, have 4th order propagating degrees of freedom. Okay, and you see them here. H is the spin 2 degree of freedom in principle, but now it may have a 4th order derivative operator acting on it in the second variation. Okay, so say in stellar gravity, yes, this term is non-trivial, and that's what gives you ghosts, fourth order ghosts. Okay. Now, what's interesting here is that you realize there are two parameters, B and C. Okay, they relate to these projections here, B and C. Okay, and if I choose them in a particular manner, I can make sure that there are no fourth order propagating degrees of freedom. Okay, so in the entire space of higher curvature gravities, there's a subspace where, at least on maximally symmetric backgrounds, we don't even have fourth order degrees of freedom. And it will be interesting, therefore, and it's a possibility now, thanks to this tool, to investigate the impact of these degrees of freedom, which we normally think are very bad for unitarity of quantum gravity. Now, there's a similar thing going on with the auxiliary scalar field. There's also a fourth order term, okay? But if the prefactor vanishes, then we don't have additional scalars. So we can even investigate this boundary condition where we demand S to be 0 and F to be 0, this term here, okay? And if we do that, we end up with so-called Einsteinian gravities as a subset of the possible theories we can study here. Good. So this, to some extent, was the last point I wanted to make, okay? So maybe as a summary of the gravity section, let me point out that the community has generated strong circumstantial evidence for the existence of a fixed point. We do, even in the gravity setting, see that non-trivial canonical mass dimensions are cancelled by quantum effects. Okay. Unlike the fermionic example where we have exact solutions, in gravity, of course, we do not have that. And the challenges which we need to address in the future is that there are many more curvature invariants available. So we need to learn on how to evaluate them on more general backgrounds, possibly include covariant derivatives of Riemann tensors and such. Okay. I had no time to even dip into the question of Lorentzian versus Euclidean signature, but this is also something where quite some progress has been made recently. And if you're interested in that, I'm happy to explain a couple of these points. So my conclusion will be brief. I started with this type of beta function and with the question as to whether quantum field theories can develop these type of interacting fixed points. I gave you an overview how this is rigorously happening at weak coupling in general 4D quantum field theories. I gave you examples where this is happening at strong coupling, both in 4-dimensional theories as well as in 3-dimensional fermionic examples, which have some similarity with gravity. And I gave you a little overview as to how the research towards asymptotic safety in gravity is standing these days. Thank you very much for your attention, and apologies that it took longer than I was thinking.
Thank you very much, Daniel, for your very, very interesting talk and very informative talk. Questions, please. I see the question from Philip.
Yes. Well, first of all, thank you for this presentation. I actually had a question from earlier. When you were looking at cancelling the del 4 term, where you had that condition B plus C over something equals 0, B over 4 plus C is 0, were you discussing the background being maximally symmetric, or after the fluctuations, the background would still be maximally symmetric?
Yes. So the way it works here is, let me try to go back to maybe one page, like here. Okay. So what we are investigating is a quantum effective action for gravity, where the quantum effective action is some general function of the Riemann tensor. And the question we are asking is, what is the RG flow for this quantum effective action? So T is the logarithm of the RG scale. And so what in practice we need to be doing is we need to compute the second variation of our action. We need to add the Wilsonian regulator term. We need to invert that object. We need to fold it with the momentum space window, the scale derivative of the regulator. This operator trace now needs to be evaluated in some form. And the objects appearing in all these expressions, of course, these are Riemann tensors and differential operators acting on these objects. So the methodology with which we evaluate this operator trace, okay, over all these differential operators acting on fields, yes, is by using a maximally symmetric background. Okay, so that's the step where when we take maybe G mu nu equal G mu nu background plus quantum fluctuations. When we now evaluate this operator trace, yes, at that step, that's the step where the maximally symmetric background choice becomes active. Okay, and so now the way it works is, remember, this is now like, it looks like, okay, it's the flow for some action. Now you can, if you want, power series, expand it into powers of curvatures with couplings in front of it. So this object gives you the beta function for all these couplings, okay? Because we can, after we've computed all these operator traces on the right-hand side, we can then compute or extract the beta functions for the corresponding couplings. That's then the set of equations which we investigate and look for fixed points and other things. Okay.
Okay, so I think what you might be saying is this. If you take, as Stella did, r plus r squared gravity,
yes,
and you perturb around flat, which is maximally symmetric,
mm-hmm,
you would get this del 4 term. Now you're saying that if you run the couplings using the renormalization group, that the coefficient of that del 4 term is then 0.
No, regrettably not. No, that's not what I'm saying. Okay, I see from where your question is coming. Let me try to answer it, okay? So first of all, let me say this. I have reobtained all of Kelly's results using FRG, okay? And I have to, yes, because it's an exact flow, so there must be a corner in parameter space where we exactly reobtain Kelly's result, okay? So those results are in there, okay? What's different here is that because the methodology doesn't force you to search for fixed points at weak coupling, which perturbation theory would demand you to do, okay? And if we do that, however, we are allowed to use these equations even in the domain of strong coupling. Okay, so this is how, just as a maybe side remark, as to how Kelly's result relate to findings from functional RG. Now, your question about B and 4C, okay? So what I was trying to indicate here is something much weaker, okay? So what I'm saying here is that I could start, say, here. I can write down a Lagrangian, which is some general function of the Riemann tensor, okay? But since it's a general function, the structures resulting out of it, so the structures which then dictate how quantum fluctuations trigger an RG flow, okay, they boil down to only, in quotation marks, a number of free functions. So I could, if I wanted, I could demand, let the Lagrangian I take have the feature that if for that Lagrangian I compute the function B and I also compute the function C, let me take the liberty of the sum of these two things to be 0. If I take that liberty, that's equivalent to saying I have written down a Lagrangian which contains higher curvature interactions. Okay. However, at least on maximally symmetric backgrounds, these will not have propagating fourth order degrees of freedom. Okay. Now there's quite some activity in this field which people call Einsteinian gravity. So that's a different activity. It's an activity motivated by this classical GR extensions of gravity, okay, where people found some interest in looking into theories which are Einsteinian in the sense that they don't have additional scalar degrees of freedom that propagate, and they don't have additional fourth order propagating degrees of freedom. Okay. And so the only observation I think I was making here is that since we look at these type of theories from a quantum angle, we are sensitive to what's propagating in them. Okay. And we see these things when we look into the second variations, and we can write down conditions so that certain things happen. So we can, for example, write down conditions for theories to be Einsteinian, which is S equals 0 and F equals 0. Okay, and these conditions will likely have the exact same solutions which people have looked into by coming from a completely different angle, okay, by generalizing Einsteinian gravities with classical higher curvature interactions. I'm not claiming that this is necessarily a feature of a full quantum theory of gravity. I'm only pointing out that, like, there are, if you try to imagine like what could be very qualitatively different and what would be important to investigate to get an understanding of what is going on, then I would say the setting where these fourth order degrees of freedom are not propagating would be distinguished, and it would be interesting to understand what happens there. Then settings where they are propagating, but maybe in different manners, just to see what's qualitatively going on. Okay, and would be very helpful, very useful to see, is this significant for the question of finding fixed points, or maybe this is not even significant for that. We don't know yet.
Okay. I'm sorry if I keep on asking a related question, but could you go back to that variation of the action with respect to the Riemann tensor twice? That's it. Now, if I were to take the Lagrangian just to be r plus r squared, and I take the background to be flat, then B and C are known. I mean, so what are they? What would they be equal to? I mean, I just do the variation. I should get a formula for B and a formula for C.
Yes, we have given, I think, reasonably general formulas in our paper. Okay, but what I haven't been telling you is what A is, what this tensor is, and what this tensor is. Okay, and so A is essentially like the derivative of Riemann versus Riemann. Okay, so in a theory which only depends on a Ricci scalar, B and C vanish identically.
Okay.
Okay. In a theory which is sensitive to Ricci tensor, C vanishes identically. And the other twos are typically non-zero. In a theory which only depends on the Riemann tensor, B vanishes identically, and A and C are typically non-zero. Okay, so like B is the object sensitive to Ricci tensor interaction, C the one which is sensitive to Riemann, and if contractions or combinations are there, then B and C will be non-zero, and genuinely A is non-zero as soon as you write anything down.
So are you just saying that if the action is just Ricci scalar plus Ricci scalar squared, that B and C is zero?
B is zero and C is zero.
So what's the big deal about getting B over 4 plus C to be zero if B and C already are zero?
Yeah, that's true. There's no big deal in that case.
Okay.
Yeah, but as soon as you have Ricci tensor interactions, it's going to be a case. Yeah.
Okay. So all right, fine. So basically, this key technical point, which is a very interesting geometric point, has no bearing on the stellar R plus R squared ghost problem.
No.
Okay, because you seem to be implying that it might.
No.
Okay.
It has, so not that one. No.
Okay, thank you very much.
Mm-hmm.
Okay, let's go to the next question. I see the next question from Alexei Koshelev. Alexei, please ask your question.
Yeah, thank you, Daniel, for your very interesting talk. Actually, I'm about the same slide as Philip, so you're just right to the point. I'm slightly confused. What you are saying here is that if I vary this Lagrangian couple of times, then I will get something like second and fourth order derivatives. This I understand, but what I don't understand is you're talking about maximally symmetric space-time. So practically speaking, it's
backgrounds. Background. So remember, okay, we use for us, it's a tool to do the operator trace.
Yeah, but so I mean, practically it's the Sitter space, yeah?
Mm-hmm.
Practically speaking, because nothing else is maximally symmetric in greater than 2 dimensions.
Yeah, it can be hyperbolic.
But let's take even simpler. Let's take Minkowski. If I take Minkowski background, then nothing higher than Riemann tensor squared can contribute. Yeah, because Riemann.
Yes, I mean, Minkowski has this slight disadvantage because, maximally symmetric background, say the radius of, say, the sphere, because your maximally symmetric background says the sphere, okay. And so the way to differentiate curvature and variance is simply by the power of the radius, because the radius of the sphere is the three-dimensional parameter in the game.
Yeah. So technically speaking,
background is now flat, of course, then I have a problem. Then
so technically speaking, on Minkowski, you cannot cook too much.
Yeah, so for Minkowski, you would do it differently. Minkowski is essentially, if it is Minkowski, then you would try to do it like an ordinary quantum field theory, because then your operator trace is just a flat momentum integral. Okay. But
now, even if it is de Sitter, what's slightly confusing to me is the following. We also were dealing for quite a time already with higher derivative series, and even specifically with infinite derivative series.
Yes.
One of the results which we have obtained, which is very simple but still quite nice, that whatever combination of Riemann tensor you can imagine, or Ricci tensor or whatever, as long as it is covariant, effectively it is the same as to write something like Riemann tensors and bunch of D'Alembertians, as many as you like, according to your mass dimension, and then again a Riemann tensor. Effectively, it will be the same. Nothing else can survive. No matter it's Minkowski or de Sitter, we also use maximally symmetric properties to derive this result. And
that's interesting what you're saying. Okay.
Yes, surely.
So I can, well, I'm not sure whether I can contribute a lot, okay, but like the angle for us. So the angle for us is that it is still demanding to find flow equations for objects which have D'Alembertians or Laplacians acting on curvature, higher order curvature operators.
Yes.
And so this is something which is technically still very, very challenging. Okay, as you have seen, of course, we are here in the universe where we don't have any covariant derivatives acting on it. Okay,
sure.
So if you tell me that there is some indication for structural similarity in the flows triggered by objects which on dimensional grounds are similar but are consist of covariant derivatives acting on curvatures, then that is interesting, because it would seem to hint at the possibility of finding RG flows for such objects. Okay.
Yes, this was kind of my question / comment about this. But what I'm really confused, because what we are showing by pure algebra is that any combination of Riemann-Ricci or whatever tensors can be, well, they cannot be really transformed to combination of covariant derivatives. But, well, in some sense, yes, in some sense, no. You can play a lot with these tensorial identities. But the point is that what we name effectively equivalent, it means that whatever we need for second variation can be obtained from the action which contains second power of curvature, and then as many as needed covariant derivatives. But what is confusing me in that particular picture, we clearly see that it is, let's say, impossible to eliminate fourth derivative, fourth order interaction, unless we go to the trick which we like very much from strings. We introduce infinitely many derivatives and then combine them to some exponent of entire function such that no perturbative poles exist.
Yes.
And there I'm confused where is it, practically where we differ. This I cannot judge immediately, but maybe you know where we differ, because I don't see eliminate on our way.
Yeah, yes. So I'm happy to have a look into your works. I may not have been aware of them, okay, and so I'm not totally familiar with how those studies in practice work, okay, but I'm happy to have a look into that. The only thing I can tell you here, okay, is that that the maximally symmetric backgrounds have this distinguished feature that they would seem to suggest that higher curvature invariance can be written down. Funny combinations. People have actually computed how these look like. Okay, so these are rather complex expressions in Riemann tensor and Ricci scala when you rewrite it. Okay, so that nevertheless, okay, at least again evaluated on maximally symmetric backgrounds. Okay, that they don't give fourth order propagating degrees of freedom.
Yeah.
Now, one more thing. Okay, so on the one side, like in C, given that like we are operating in a very complicated theory and we need to make some simplifications, and doing the simplifications of using maximally symmetric backgrounds is here the tool which allows us to make a step forward, but it's only a tool, okay, and it has limitations. Okay, so I wouldn't be surprised at all if, like on more general backgrounds, yes, that certain theories which look as if they don't have fourth order propagating degrees of freedom still will develop them if the backgrounds allow a bit more structure than maximal symmetry. Okay, so I wouldn't be surprised at all about that. Okay, it still means, however, for what it's worth, in the sense of making an investigation into some non-trivial version of gravity, okay, that still we can use that to some extent, okay, but of course it's as a tool and as an approximation, it is going to have its limitation.
Yeah, I see. Yeah, I would be happy to continue the discussion after in more technical terms, because it's really confusing to me.
Yeah.
Yeah, thanks a lot.
Yes, welcome.
Okay, let's go to the next question. The next question is from Hong Wu.
Yeah.
Hong, please ask your question. Yes.
Yeah. Okay. First, thanks for the nice talk. I have a question. So because I work in the SFT, so where is the contribution of ADSFT in this talk? Because this talk you say that ADSFT.
Yes. Okay. Yeah, that's a good question. So you're wondering where a contribution to where ADS CFT in some sense has contributed to what I was reporting here. Okay, so let me try to go back to that. Okay, and so the point I was trying to make when we decided to look into these critical fermionic theories is that, let me see, maybe I haven't, okay. So the point where it kind of works is that think of ADS4, CFT3.
Yeah.
Okay, so there are these really seminal examples going back to Klebanov and Polyakov, who showed that critical bosons in 3D used on the CFT side, okay, relate to a certain version of, I think it's called type A higher spin gauge theories a la Vassiliev. Okay, and so then briefly thereafter, Zeshkin and collaborators managed to actually also figure out that critical fermion theories at the CFT boundaries correspond to the type B higher spin gauge theories on ADS4. Okay, and there is a big review like looking into some of the, okay, so this is really something which has triggered quite some work back in the days, like Maldathena and his back then PhD student Jiboidev looked into what can be learned from CFTs in 3 dimensions and how these relate from that angle to higher spin gauge theories. Okay, and it was quite interesting to see kind of how certain structural things are so constraining already that relatively strong statements about the related CFT 3-point functions and stuff can be extracted. Okay, and so in this context, I was trying to make the point that these new types of 3-dimensional critical theories, which are now those which have a non-trivial 6 fermion interaction. These theories on the CFT side, they are different. Oh, sorry. On the theory side, they are qualitatively different because they do not have chiral symmetry. Okay, and so it is interesting, and that question has not yet been answered. So I've started discussions with people who know a bit more on the ADS4 side in this field. Okay, but I think it would be very interesting to see when you give up chiral symmetry on the CFT side, okay, what is this going to dictate for higher spin gauge theories on ADS4? Into what does that structure translate? Because there needs to be some sort of dual, and it would be interesting to see what that is.
Okay.
But if in 3 dimension or in 5 dimension, what happened?
I don't understand the question.
What do you mean exactly? Like, so say in the ADS CFT works by having a CFT on the 3D boundary, okay?
Yeah.
And so this 3D CFT in one case, okay, so let me try to show you the plot. Okay, like this is a funny plot, I'm afraid, but it's this one here, okay? So what is V prime? V prime is the first derivative of the action, the fixed point action. Okay, so this is, so, and I plotted it in a slightly funny scaling because I wanted to plot it from, Z is psi bar psi. I wanted to plot it from psi bar psi, taking values between -infinity and infinity. So this blue curve here, in a sense, that's really the fixed point boundary condition on, yes, the CFT fixed point boundary condition, and it has chiral symmetry, and chiral symmetry in this plot means that it is rotationally symmetric with respect to the origin here. Okay, and the point I wanted to make is that now we also find these ultraviolet fixed point solutions which are not chirally symmetric, and I gave one example here, which is the red curve. Okay, and you see it's no longer rotationally symmetric, and that's because it is not chirally symmetric. So yes, but it is still a totally valid fixed point solution with certain features. Okay. And so, of course, I would expect that the gravity dual, which now has a bit to do with higher spin gauge theories, of course, okay, that theory will take some notice of the fact that the boundary condition is no longer having chiral symmetry. And I was just wondering about like what actually that is. Is this something which could be of interest from the higher spin gauge theory point of view? That I don't know. I don't know what the answer is to that question.
Okay.
Okay. I don't see no more questions because we are a little bit over time. So I think that the people a little bit tight. But in any case, thanks the Daniel for I would say for excellent talk. Yes, I learned very interesting stuff. I also would like to ask you, maybe I will write you a letter because we are a little bit over time. So thank you very much once again. Thank you for everybody. Okay, bye-bye.
Thank you very much.
Yeah, thank you very much. It would be great if you can send me slides. Usually we upload them on the website.
Yes, absolutely. I will do so.
Yes.
Bye.
And I will send you email with what I meant.
Yes. Yeah, that's good. No, I'm happy to stay in contact, and maybe we can discuss a bit offline and give me a bit of time to have a look into your papers and understand your question. Okay, so maybe that's.
And maybe I will ask you what, because people already finished. I supposed to ask you a question about supersymmetry generalization, because usually there is supersymmetrical counterpart of the Weiergross model. So why you decided to remove all bosonic sector? Is some special case, or because, for example, nonlinear sigma model, the Schwarz is a counterpart from fermionic part, but
Okay, so I'm sure you know more than I do in those theories. Okay, let me tell you this. We look into Vesumino model. So Vesumino model in some way is the way I think about Vesumino. Okay, it's like a scalar Yukawa model. Yes, scalar fields, Yukawa fields with Yukawa interaction. What has this to do with for Fermi? You can think, of course, you know that people like to think of the for Fermi theory as maybe a Gros-Neveu Yukawa model, where you bosonize psi bar psi. Okay, and so in the bosonized version of that theory as an infrared scalar Yukawa fixed point. Okay, and so that's then a natural theory to supersymmetrize. And then you get the Vesumino model. Okay, we did investigate the Vesumino model some 10 years ago using the same type of methodology. Okay, we also see a line of fixed points there. Okay, so this is very similar. Now, what I'm not aware of, and maybe you can help me with that, is I'm not so sure how we can supersymmetrize directly the for Fermi theory. Okay, maybe there's a trick to supersymmetrize it in the fermionic without bosonization, if you see what I mean.
Well, I hope maybe I can answer to your questions. Yes. Okay. Okay. Let's be in touch.
Okay.
Yes. Thank
cool.
you. Thank you very much for your
Yes. Thank you, everybody.
Bye-bye.
Okay.
Bye. Bye.
Yes, thanks again. Bye.
Bye, Alexei. Thank you very much. Bye, Huang. Bye, everybody, for.
Thank you. Goodbye.
Very interesting questions. Yeah. Bye-bye.